And now it's my pleasure to introduce Antonio, who some of us already met in Toulouse last year. And he will be talking about time-varying semi-definite programming, geometry of the trajectory of solutions. The floor is yours.
Thanks, Felix. Good morning, everyone. It's nice to be here, or virtually at least. Okay, so the object of this talk is the research that I have been conducting during the first part of my PhD in the Czech Technical University in Prague, under the supervision of Didier Henrion, Vyacheslav Kungurtsev, and Jakub Marecek. And I'm also part of the optimization group led by Jakub of the Artificial Intelligence Center of the Computer Department of the CTU. Okay, so let me go straight to the topic. Time-varying SDP is semi-definite programming, so linear optimization over the cone of positive semi-definite matrices, where the data of the problem and hence the solutions depends on some time parameter that we can take in some interval. And here I put some of the most notable references. So this problem is has been studied before. And the first reference...
Antonio,
yeah.
can you go full screen with the slides? I think for some people it might be a little bit too small at the moment.
All right, so because you see my whole screen then?
Yes,
I thought...
yes, exactly.
Okay, how about now?
Yeah, that's very good. Thanks a lot.
Okay, thanks for stopping me. I don't see what I'm sharing, so okay. So yes, I was telling about these references that I've put here. So the first one is Parametric SDP by Katja Scheinberg and Donald Goldfarb, in which they considered an SDP where the objective function linearly depends on a parameter. And they studied the optimal objective function value as a function of time. And they start extending some notions of linear programming to SDP as the one of optimal partition, which is basically a notion that characterizes the solutions. And a more recent paper that keeps on working on these ideas is this paper by Hauenstein and others, where they keep on focusing on linear dependence from the parameter. And they keep on studying this notion of optimal partition, and in particular, they focused on the idea of nonlinearity interval. So I'm citing this paper mostly because many of the results that they have there, we managed to use them in our research. The last reference I have here is Time-Varying SDP by Ahmadi and El-Kadir, in which they consider a bit more broad framework where the SDP is polynomially dependent on a time parameter. And they showed that in this setting, if one restricts to polynomial solutions, then the optimal value remains the same. They also showed that if one looks for a polynomial solution of a fixed degree, this can be found by solving an SDP of a tractable size. Okay, so we build a bit upon this background, and our main goal was to try to characterize the trajectory of solutions to time-varying SDP and try to understand which are the possible irregular behaviors that this trajectory can have. I'm talking about trajectories because, of course, in time-varying SDP, you have a solution, but the solution is depending on time, so is drawing some trajectory. And the idea was inspired by this textbook, but in which the authors, Goodhat and others, classified the point of like solutions to parametric NLP. So the approach was kind of the same. So okay, so this research resulted in a paper which is available on arXiv in a preprint and is actually current under review. And the original contribution of this paper are the definition of 6 types of points in the trajectory of solutions. And then we proved a classification theorem in which we state that only these 6 types of points can actually happen and appear. Also, under generic assumptions, there are actually only 3 of these types of points that can show up. And okay, so the usefulness of these contributions should be that, of course, we are adding some more knowledge to the time-varying SDP problem, and trying to understand what can go wrong and also why. And this knowledge would be useful also for algorithmic designs. It's obvious that if one, for example, wants to track the trajectory of solution, needs to know what can happen. And this also prepares the way for a future research on time-varying POP. So if you have a time-varying polynomial optimization problem, one approach is you can try to use the moment sum of square hierarchy, and this will lead us to considering a series of time-varying SDP. So this study of the solutions to time-varying SDP can somehow be extended to time-varying POP. And this is actually the next step for my research. So here I have a summary of my talk. I will give you some short crash course on SDP properties and set valued analysis. And these are the main tools that we need to show the main theorem. I will then expose these 6 types of points, show the main theorem, and then I would provide a sketch of the proof and also some example to illustrate the theorem. Okay, so here I'm recalling some facts about the geometry of the spectrahedron. So spectrahedra are the feasible set of SDP. And so they are a fine section of the positive semi-definite cone. A face of a spectrahedron is a set that can be described as intersection of a spectrahedron and a supporting hyperplane. Whereas we define an extreme point as a 0-dimensional face. Why faces are important? Well, simply because the optimal set of an SDP is always a face. Okay, so this fact that I'm citing now is quite intuitive. The solution is unique if and only if the optimal set is an extreme point. Of course, if this wasn't true, then you would have a positive dimensional set, optimal set, so you wouldn't have optimal unique optimal solution. And this fact is actually generic. So the solution to SDP in general are unique and hence extreme points. And I will give you more detail about this fact. Okay, so basic properties about SDP. If you have a primal dual pair of SDPs, there are first order optimality conditions available, known as the Karush-Tucker conditions, the KKT conditions. And so these conditions are in general sufficient for convex optimization problems. Under the assumption of strict feasibilities, these conditions are actually necessary and sufficient. Strict feasibility means that both the primal and the dual problem, they have a strictly interior point. Okay, so let me discuss some properties again and give you more detail about uniqueness. So we try to answer the question, how do we know that a primal dual solution XZ is unique? Okay, so we say that a pair of primal dual solution XZ is strict complementary if the sum of the rank is equal to n, where n is the size of these matrices. And we say that the primal solution X is primal non-degenerate if the following fact is true: the kernel of the linear operator A that defines the affine space that defines the feasible set, summed up with the tangent space of the positive semi-definite cone at the point considered X. These spaces sum up to the whole space of symmetric matrices. The dual property is just we substitute the kernel with the span. So you take the matrices that defines this linear operator and you take the span of these. Okay, so I point out that there are linear algebraic conditions that are equivalent to this characterization of non-degeneracy. So these are properties that one can actually numerically check. And the interesting fact about non-degeneracy is that the existence of a primal non-degenerate point implies the dual uniqueness, and the dual property is also true. And under strict complementarity, actually the converse is hold. So these properties, strict complementarity and non-degeneracy, actually hold generically. This was proven by Aliza and others. And this implies that the solution uniqueness holds generically. And this is what I was mentioning the slide before. Okay, so to give a bit more insight on these properties and their relationship with uniqueness, I have this slide in which, so we take the KKT conditions here on the left, and we rewrite them as the form in the right side here, and we kind of divide these conditions and regroup the first three conditions under this request that the function f is vanishing. So again, Aliza and others prove that under strict complementarity and primal non-degeneracy, the Jacobian of this function is invertible. So this fact about the invertibility of the systems kind of gives you some sense of why these properties should ever imply the uniqueness of the solution. And actually, this result would be useful for proving our main theorem. Okay, so at this point, I'm ready to present the main objects in which we are interested in. So we considered a pair of primal dual time-varying STPs, parameterized by some parameter. And of course, the main objects are the feasible set, the optimal value function, and the optimal set. And in particular, here I'm pointing out that these sets are actually set maps, in that you have the map that for any given point in time gives you back the feasible set or the optimal set at those times. In particular, we are interested in the optimal set maps. So since we are talking about set valued maps, we need to use tools from set valued analysis. So here I'm giving you some basic tools from set valued analysis and definitions. So a set valued map is nothing but functions that instead of having images that are values, it has images that are actually subsets. So for this type of maps, we can define the inner and outer limits. I think this is much clearer from the picture rather than from the analytical definitions. But anyway, we define the inner limit of a set valued functions f for t that approaches some fixed point t bar as the set of points for which at any time sequence that you find approaching this fixed time t bar, you have a corresponding sequence of points that belongs to the image of this time sequence and that approach the such a point x bar. The outer limit is just the same thing, but instead of you replace this for all operator with an existing one. So this gives you that basically the inner limit here would be the blue dot, while the outer limit would be the green segment, because it's clear, right? Like for the blue dot, if you take a sequence approaching t bar from the left, then the only limit that you can have is this dot. While for the green case, you just are content of having one sequence of time. So any sequence from the right, you can find a consequent sequence approaching any point on the green line. Okay, so therefore we define an inner semi-continuous function as a function for which its inner limit coincides with the image, and the outer version of this is that it's the same. And we say that a function that is both inner and outer semi-continuous is Penleve-Kuratowski continuous. We will just say continuous because it will be clear. We are talking about set-valued continuity notions. Again, here the pictures are much clearer. So the first picture is an example of a function that is neither inner nor outer semi-continuous. Then we have an inner semi-continuous function, an outer one. and finally, you have a function that is Penleve-Kuratowski continuous. Okay, so we needed these continuity notions in order to being able describing the optimal set maps. So here we go. Here I'm listing as a list of the most kind of interest results on this. So the first theorem says that if the problem data are continuous, then both the primal and the dual feasible sets must be outer semi-continuous. And if you then add the assumptions of strict feasibility and the fact that the linear constraints defining the feasible set are linearly independent, then also the inner semi-continuity holds. The dual version of this result was proved by Hauenstein and others, and we have an original proof of the primal version in our paper. But then we are more interested in actually studying the optimal set maps. And under the assumption of continuity of the data, outer semi-continuity always holds also for the optimal set maps. Actually, in particular, this implies that whenever your optimal set is single valued at some point, then at that point, it also must be continuous. Okay, so these were all positive results. So under some assumptions, this inner and outer continuity holds. But for the optimal set maps, actually, we have a negative result that basically tells us that inner semi-continuity for optimal sets can actually fail. And furthermore, Mankres show that the subset of points in the optimal sets where you have a failure of inner semi-continuity is actually the union of countably many sets lower dense in T. So, so these were like the first results on the optimal set maps, and so we tried to say a bit more than this. So we tried to investigate more what happened to the optimal set, and also we are interested in what does it mean that a failure of inner semi-continuity happens. Okay, so this is the settings that we took. So we assume to have a primal dual pair of time varying STPs parameterized by some time interval T. And we assumed the standard hypothesis of LICQ. So the matrices defining the feasible sets are linearly independent. And the strict feasibility for every point in time. And finally, we assume that the data of the problem must be continuously differentiable with respect to the time parameter. So in this, we have took a setting that is somewhat more general than the previous work that has been done on parametric STP. So we try to be as general as we could in this study. Okay, so here I will start exposing and defining the type of points that we discovered and that we classified. So let me repeat the goal. The goal is to classify points. In this case, we are considering the optimal set map, P star. So we classify points considered as a pair of a optimal point X star and the time at which that problem is considered. And our approach was the following. So we considered a trajectory of solution such that this trajectory is given by a smooth branch of a single valued curve. So what we are doing is considering the case in which the trajectory of solution is behaving in a nice manner. And the first questions that we want to answer is, how can we actually be sure that the solutions is actually behaving well? And the answer is given by actually the same properties that I've been discussing before, so strict complementarity and primal dual non-degeneracy. And, and the second question, which was the most interesting one, was how actually can this good behavior be affected? So what can happen at the trajectory of solutions? So the answering to these questions led us defining 6 types of points, where the first type is kind of the nice one, so we called it regular points, and all the other one are type of points for which some kind of irregular behaviors appears. Okay, so you see them listed here. I will now go through each of them and illustrate with some cartoons. Okay, so regular point is simply a point considered at some time t star, for which the optimal set map in a neighborhood of this point t star is single valued and hence continuous. And we require that at t star the optimal set map is differentiable. Okay, so this is actually the most kind of general case. You can see here an example. So I have a Cayley Spectrahedron, and I have cut this right vertex with some hyperspace. And then we are considering an objective function that you can imagine basically rotating around the screen, like parallelly to the screen. So the solution would be moving along this green trajectory. When this green trajectory is moving on one of the surface of the spectrahedron, then the solution would describe a smooth trajectory. So this is one example. Another example is here is clear. For example, you have this extreme point, and you can imagine that even like if you are at that extreme point, small perturbations of your parameter would keep you there. So the solution would be constant and then differentiable. Okay, so this was the most plain situation. Let's look at more interesting things. The first thing that can happen is that you have a loss of differentiability. And this is caused, for example, in the situation that we were describing before, by the solution that is moving along the green line suddenly would hit this extreme point, this vertex here, and consequently stop there and staying there for some time. So the picture that is then produced is something like that. So there is a loss of differentiability. So this is the first degenerate phenomenon that can occur. Another thing that can happen is that you have a loss of inner semi-continuity that we were mentioning before. We classified and defined these points as discontinuous isolated multiple points. So again, here it's worth looking at the picture. So imagine, as the situation before, we are moving along this green curve. When the objective function ends up pointing downwards, then the optimal set would be this all blue edge. And consequently, the image that you get is this one. So there is a smooth trajectory that, however, at some point becomes multi-valued. So this implies you have again loss of uniqueness and loss of inner continuity. There is another case in which this happens. Again, geometrically, let's assume now that we have this vertex here on the left as a solution, and then our objective function rotates clockwise. At some point, we then hit this whole edge as an optimal set, and immediately afterwards, we just move to the other right extreme point. So then the situation is depicted in this other plot. So what is worth pointing out here is that these two situations, even if they are both loss of inner semi-continuity, are a bit more different in their nature. And the reason is that in the case here, in the case A, you can actually find a selection of this set valued map so that you preserve continuity in a way. And this has some importance algorithmically, because if you are on a left neighborhood here and you try to lose local information, then you won't be misled by this local information, because you wouldn't even look at these spikes here. Whereas in this case here, you would be totally misled by this local information, that if you try to evaluate the solution here. So here the nature of the discontinuity is more dramatic. Okay, then there is the fourth type of point, which is discontinuous non-isolated multiple points. So the difference between this case and the one before is that here the loss of uniqueness is permanent. So for a while we keep on having multiple solutions. And how this can happen, for example, here I took again the Cayley Spectrahedron and just cut the rear surface with an hyperplane, so that here on the rear you just have a flat triangle. So when you try to follow the same trajectory as before, when you hit this edge here, you will be staying there for some time until you hit some critical point in time. So again, here the difference is that you don't have an isolated multiple point. You have something that is non-isolated. So again, the nature of the irregularity is harder here. Then we have continuous bifurcations. We can say that what happens is that there is a loss of uniqueness. And again, this loss of uniqueness is remaining for some time. But the key difference is that this loss of uniqueness happens in a continuous way. Again, here you have an example of how this can happen. This time you have our objective function is still rotating, but this time like counterclockwise. So at the beginning, we are staying at this vertex here. This is the optimal solution. And then at some point at a critical time, we start moving along this surface. And when we move here, the optimal solution will be given by some positive dimensional segment, some one-dimensional segment. So then the plot is actually like this, a bifurcation. Okay, then we have the last type of points, which are more like counterintuitive, and they are a bit crazy in their behavior. So I would like to tell you how we arrive to recognize such a point. So basically, if you rule out from what can happen all the types of points that we discussed before, you kind of see that there is another possibility. And the possibility is that, again, you have an irregular accumulation point. This is how we call it. And we actually then showed that there are cases in which this strange behavior can arise. So we defined an irregular accumulation point as a point for which there is a sequence of time converging to the time considered. And each of these of the time of this sequence is either a continuous bifurcation or a loss of inner semi-continuity. And in these examples that I'm showing you, you have the case of each of the sequence of times approaching the time t star. They are continuous bifurcation points. And such a crazy behavior actually can arise quite simply by simply put some dependence that is trigonometric here. So yeah, this can actually happen. Okay, so now I actually have the main theorem. So at this point, I would like maybe to ask if there are any questions, maybe some curiosity about the types of points. Okay, then if not, I will just continue. Okay, so here you can see our main theorem. The main theorem states that under, like, if you consider a pair of time-varying STPs satisfying the assumptions that we mentioned before, so LICQ, strict feasibility, and the continuous differentiability of data, then only the type of points that we defined, these 6 types of points, can appear. And then there is maybe a more interesting result that states that if in this parameterization interval there exists a time for which you have a strictly complementary and primal dual non-degenerate optimal point, then the only points that can appear are either regular points or non-differentiable points and discontinuous isolated multiple points. So the first 3 types of points that I showed you. And the interesting thing is that these the degenerate types 2 and 3, in this case, only happens in a finite number. Okay, so let me prove this or show you how is the strategy to prove such a result. Okay, so this would show the first part. Sorry, there is a typo here. This should be part 1. So proving that the types of points are the types of points that we defined are the only possibilities were proved by just using some logical case partitions. So we try to put together all the possible cases. So we first consider, again, as I was saying, we are considering a trajectory of solutions that is behaved regularly, and then you look at what can go wrong, right? So we consider some time t hat, and then you divide the case whether at t hat the optimal set is single valued or multi-valued. And then you have another partition that partitions the cases of what happens in a left neighborhood of, sorry, in a right neighborhood of this t hat. And okay, and then this is clear. So these are mutually exclusive, and they complete all the cases. And then the strategy was just to combine these partitions, getting again a 6 cases partition of all the possibilities, and then it's pretty easy to derive from each of these cases the definition of the types of points. So in this way you prove that the 6 types of points are the only types that can appear. Okay, so here I think there is a bit more interesting part, which is showing why the second part of the theorem is true. So why only 3 types of points arise if you assume that there is a point in time for which you have a strict complementary and non-degenerate solution. Okay, so in order to do that, we first need to a couple of lemmas. And in particular, this lemma actually also shows us why the answer to the question, how can we be sure that the trajectory is regular, so is answered by this lemma. Okay, so the lemma says that if you take a pair of time-varying STP with data continuously differentiable, and you're supposed to have a unique optimal and strictly complementary primal dual solution at some time t hat, and here you can, since you're assuming strict complementarity, you can remove unique and says like non-degenerate, so it's the same thing. Under this hypothesis, you can use the implicit function theorem and says that there exists a neighborhood of this point t hat, such that all your the optimal trajectory is described by a unique and smooth curve, at which all the primal dual solution is also strict complementary. And the proof of this fact is basically direct application of the implicit function theorem. And here you have a sketch of this. So you take the KKT optimality conditions, and as I was saying before, if you have uniqueness and strict complementarity, then the Jacobian of this function is invertible. And this means that you can define, you can find some curve x of t, y of t, z of t that's satisfying this subset of the KKT conditions around t. So then the only thing that you need to prove now, is that this solution has to be positive semi-definite. So the thing is that if this wasn't true, then this means that your KKT system wouldn't have a solution, and then implying that the problem PT was infeasible. But this would contradict the primal and dual strict feasibility assumption. So then x of t and also z of t, they has to be positive semi-definite, so they are actually yes, they are actually a solution and an optimal points for the problems. Then here I'm not mentioning there is another technical thing that you have to check, that is that these two solutions are strictly complementary. But this basically follows from the fact that this solution you are assuming here, you're assuming it to be strictly complementary, and this implies that if you are moving along some continuous trajectory from these points, you can restrict the perturbation so that the strict complementarity property is preserved. Okay, so then this is instead the part that tells us about the finiteness property of why there are only finite degenerate points under the assumption that you have a strict complementary and unique point at some t hat. So you assume this was proven by Hammerstein and others. You assume that you have a value of the parameter where you have both strict complementarity and primal dual non-degeneracy. And this implies that the set of values of the parameters where you don't have these properties, so where the optimal primal dual solution is not unique nor strictly complementary, has to be finite. The proof of this relies on the fact that the set of points where we can't apply the implicit function theorem is a constructible set. And then we use the fact that a constructible set is either finite or has a finite complement. And since the complement of the set we are considering is the set where you actually can apply the implicit function theorem, this set can't be finite. So the complement, which is the set that we are considering, has to be finite. So this implies that the again the number of points where you have either a loss of uniqueness or a or strict complementarity has to be finite. Okay, so then when you put together these results, you get, I will go back to the theorem, you get this second part. So you know that if there exists a strictly complementary and primal dual undegenerate optimal points, then you have to have some regular points around this, and then in your time parameterization, you only have a finite number of points in which, let's say, bad things can happen, and this again lead you immediately to conclude that these are the only possible cases. So I mean, you can have more. This was like more a sketch of a proof, so you can look at the preprint to have more details on the proof, and on the it's more, there are more of course technicalities. But what I want, the aim of my talk here is to kind of convince you that this is what happens in general to SDP, and this is what can happen. So for that, I have the simplest examples I could find. So here you have the Cayley Spectrahedron here, and you're taking an object functions like this that is depending on time, and the optimal set maps is described by this this equation here. Let me describe what happens. So if you look at this this example, you see that for if you're considering t between -2 and 3, you only have regular points except for 0 and 2. And in fact, we are in the second part of the theorem, because, for example, at t -1, you would have a strictly complementary and non-degenerate primal dual solution. So we are in the second part. And here you also see that you only have a finite number of irregularities, and these are happening at t equals 0 and also t equal 2. So both at t equals 0 and at t equal 2, you have a loss of strict complementarity. And this led for t0 to a discontinuous isolated multiple point. And again, this is just coming back here. It just means that we are hitting an edge, a whole edge of the spectrahedron. While again, the reason why we have a loss of differentiability is that we are hitting one of the vertex. Okay, so this example was meant to convince you that this, especially the last part of the theorem, is, is this what is what happens in many cases. Okay, so I have I think I have did what I promised, or I hope so. So I showed you the definition of these 6 types of points, and showed you this classification theorem. So again, to terminate, just the next step for the research in this field for me would be considering time-varying polynomial problems, and using the moment sum of square hierarchy, try to study the trajectory of solutions to time-varying pop, and see if there are also there properties that implies a regular behavior, and if can we say something about yes, the degenerate behaviors that can arise there. Okay, so with this, I've concluded my talk. So I thank you for your attention, and I would welcome any questions that you might have.
Thanks a lot, Antonio. Nice talk.
So maybe, Antonio, if I may just ask one naive question. Can you give us some examples of time-dependent STPs that people are interested in?
You mean like some applications, or?
Yes.
Yes, for example, one thing that we thought of is there are applications of, this is interesting because it's not that straightforward to get, but there are applications arising from computer vision, for example. So there is a problem which is the background subtraction, and where there is the problem of you having a video and you have maybe a moving background and a foreground. The background is maybe moving a bit slower than the foreground, and you want to separate these. And the thing is that you can cast this problem as a time varying STP. So that's the way you do it is you have to. So you first cast the problem as a rank minimization, and then you have to use some nuclear norm results to then transform this problem in time varying STP. But also, again, the main idea is that when you have time varying pop, then you will most probably have to use time varying STP. So that's also the application. So actually, I'll this week I'm moving to Toulouse, where I will doing some research on that with Didier and Rian for a couple of months. So.
And may I just ask one more question? In your basic model, in the primal problem, both the matrix C and the right-hand side vector B dependent on time.
Yeah.
So if you just change it that only the vector C depends on time, do you lose generality, or is it? I'm just wondering why the specific form of the time-dependent problem.
Yeah, right. Well, I think that the approach that we had is just, try to, to take the most general case. So I guess that's.
But in the most general case, the matrices would also
depend. If you would lose generality, but definitely you gain in generality if you consider both the C vector and the B vector.
Yeah, but I mean, in principle, you could also consider the data matrices to be time dependent, the AI matrices.
Yeah. Yeah, so that yes. Okay, so on that, yes, instead that's a lack of generality. So we restricted ourselves to the case of the A matrices being a constant. And the reason is that, there you would have, we would have to take into account like degeneracies that, for example, may arise from the fact that maybe at some point in time you lose the LICQ property. So
okay, now thank you very much, Antonio. It was very interesting.
Okay, thanks to you for the questions. And if there are others, please.
Maybe I would have a question. Thank you very much for the nice presentation. So maybe I have a little bit naive question coming back to the last example. Yeah? In that last example, you see that sort of the bad things happen only in 2 points. So in other words, on a set of measure 0, right? So now if I'm thinking of a practical example and a corresponding solution strategy for such a time-dependent STP, I would probably choose sort of an appropriate time discretization. And then for such examples, my feeling would be that I never hit such a point, right?
Yeah.
The probability is 0. But of course, I guess what could happen is that what I would observe then in a trajectory in the bad cases, that somehow the trajectory jumps from one branch to another one, right?
Yeah.
But the question is, do you also have examples in mind where somehow the bad things happen somehow on a set of which is not of measure 0?
Yeah. So yes. So I have them. I didn't thought I would make it so fast, so I didn't include it. But basically, okay, I want to come back to this slide. If you this happens in the first point of the theorem, right? Like in the first item. So in general, if you don't have this assumption here, so not having these assumptions mean that actually at any time of your time parameter, you either don't have strict complementarity or you don't have non-degeneracy. So you have degenerate points. In this case, and I have examples of it, you can get the situations that I was describing before. So for example, yes, for example, this one is easy. So you see that this gray part as not measure 0, like, and all the points here are irregular in a way. It depends on, I mean, here we define irregular as we see non-uniqueness as a type of irregularity, let's say.
Sure.
So here is an example, right? Like it's really straightforward. I just take the Cayley Spectrahedron and I cut it, and I took, I think here is a objective function and it's quite similar to the other examples. And also this one, right? Like this is, you literally have this plot here is generated by such an example.
Yeah, okay, absolutely. Yeah, I see.
But yes, but then.
But these examples are somehow handmade. They are constructed to be bad, right?
Yeah, exactly. So that's what that's why it's important to have this twofold kind of theorem, and probably we should want to say that the second part is what happens really, right? And again, this is related with the fact that sorry, let me go here. This property of strict complementarity and non-degeneracy, they are generic properties. So yes, indeed, the process of my research was first studying some examples, but then really try to imagine what was possible. So then I would, create examples in order to that things to happen. And after having done that, then I constructed this kind of cases partition to show that actually there are no other cases possible.
Yeah.
And that's it. And the final remark I would like to say is that our classification was made, again, considering a trajectory of solution that is first like nice, and then we looked at what could go wrong. But then, of course, you can have, in principle, even crazier behavior. For example, if you have, I don't know, a one-dimensional optimal set, right? Which at some point bifurcates and becomes like two-dimensional, for example. So this would be kind of a generalization of the bifurcation. It depends on, but again, this would still be not a thing that happens generically. So yeah, the lesson to learn here is that when you have time varying STP, what happens normally is this second scenario in which you only have a finite number of points, and at these points you can only have non-differentiability or a loss of uniqueness.
Okay, thank you for these additional explanations.
Yeah.
Very good.
Hi, I would also like to ask a question. Is that okay?
Yeah, of course. I mean, fine.
Ciao, Antonio. Hi. Yeah, I'll be happy when you come to Toulouse, and thank you for your talk. And my question was about when turning from one parameter t to multidimensional parameters. So once you have differentiability in one direction, I would assume that means you have you can directionally differentiate. But do you know how much you might lose, or how much harder it would get when considering multidimensional parameter sets instead of just
honestly, we really never considered this this case. I mean, yes, I mean, we didn't think about the problem, so I've never thought about this actually.
Okay. Yeah, I was wondering, since maybe you can.
I don't even know in general if, you know, if how. I mean, I guess there are many applications in which one can have dependence on many parameters. But yeah, for STP we didn't focus on that. I guess it's kind of a field that is too let's say new for having, you know, like there's still a lot to study for the univariate case. So I guess there would be a lot, like a bit crazier than here. Maybe not so crazier, but who knows?
I mean, I would assume that your work is a very good starting point because it allows you to do directional derivatives.
Yeah, so the idea was to kind of maintain a general but not too general framework, and yes, and start getting, you know, like some solid ground where to build. So there is definitely more work to do, but yeah, we have some foundations at least.
Yeah, I found it very nice, and thanks for the nice pictures and explaining the several cases. I liked it a lot. Thanks. Grazie.
There you go. All right, so I guess I don't know if there are some quick questions. Maybe we can, but otherwise maybe we can go for, I don't know.
Hello, sorry, really naive quick question, if I may.
Sure.
Yeah, so I connected a bit late, so maybe it will be really quick to answer. I noticed you ideally want uniqueness, and Corb is calling me right now. Nice. Ideally, you want uniqueness and strict complementarity for differentiating, right? And my question is, can you ensure one of these properties without actually solving the problem? Like, can I look at the data ABC and say, like, okay, this one's gonna be unique, like it's gonna have unique solution? Or do I actually need to, I mean, the strict complementarity, I guess I need to solve it probably, but...
what you can do is, for example, if you want to check the primal uniqueness of the solution, you solve the dual problem. And if you find a non-degenerate solution, this implies that the primal solution is actually unique. However, if you find out that this dual solution is degenerate, this does not imply that the primal solution is not unique. Again, however, like this is answered by this slide, basically. Yeah. So now I'm talking about the first box here, right?
Okay. Okay.
However, you can also, like, you can solve both the primal and yes, but the problem is that you have to still to solve the problem, right? So you have to solve the dual problem, and so if you want to have information before solving, it's a bit it's a bit hard, I guess.
Yeah. I see. Yeah, I was hoping
I think that the only thing you can do is really solve the dual and hope to find a non-degenerate in that solution. In that case, you know that the primal is unique.
Okay. Thank you very much.
Sure. Okay, so I don't know if there is a quick question maybe, or maybe it's time to, I don't know, go.
I think that's it with the questions.
Yeah.
Or at least it seems like that. So once again, thank you very much, Antonio, for this very nice talk.
Yes.
Then I would say we meet again after lunch.